So every column should have uh, a capacity for a combination of two things: vertical load applying and moment acting over this. Now let's after discussing concept of uh, this is called moment interaction diagram, or simply interaction diagram, or load moment interaction diagram. Now let's uh, go back and start from concentric load capacity. This is a cross section of a column. This is a width. We will name it H, and this is depth. Let give a name B. These two bars, maybe 3 bar, 4 bar, but generally I will give a name AS. And steel here, longitudinal steel here, I will give a name AS dash. And AG is the gross area. This AG is the gross area equal to H multiplied by B. AST is the total area of steel, mean AS dash plus AS is equal to AST. And AN is the net area of the section, mean AG minus AST, mean total area minus area of steel. So AN is the net area, and AST we already discussed equal to AS dash plus AS. Now suppose a load applying over the center. Now suppose a load applying over the center and whole of the section come under compression. What will happen? The concrete will come under compression, and maximum ultimate strain will occur epsilon U. It will be a uniform compression. If there exists steel, say like there exists steel, these steel and here, so the compression supported by these steel bar will be equal to this, will be represented by this line, and it will be equal to AS into Fy. And the compression come because of these steel. Suppose I am giving name AS dash into Fy, and the net compression force because of the concrete, it will come on center, and it suppose I'm giving a name CC, and it will be equal to 0.85 FC dash into net area of this section. So net area is equal to AG minus AST. So when the load applying exactly on its center, and suppose there remain concrete and steel, so generally for a case like this, three reaction forces will act. One is because of this steel line, second is because of this steel line, and third is because of the concrete. I given a name, I represent overall effect of these steel on a single force. And suppose here I represent given 2 bars, but if suppose it's more than 2 bar, again I can represent it by a single force like this. Remember, the concrete will fail at its ultimate capacity FC dash, but for calculation purpose we taking 85% of FC dash, or and that is average value. I hope everyone is clear about this, why I'm taking average value instead of ultimate value. Now the nominal eccentric load capacity Pn for this case will be given as Pn is equal to 0.85 FC dash into Ag minus AST. Second is AST into Fy, and this AST into Fy. AST mean both AS dash and AS. So if I add both of these, it will be the AST into Fy like this. 0.85 FC dash into Ag minus AST plus AST is equal to AS plus AS dash into Fy. So total capacity for this case will be equal to this equation. Remember, here I assume the condition when the load exactly applying at its center point, mean here. Now let's come to a problem. We have a section 20 by 12 inch and P and load applying outside the column at a distance E. Here we have two number 9 bar here and two number 9 bar here. So total are four number 9 bars. This cover is 2.5 inch and this cover is also 2.5 inch. Now the question given information is size of the column is 20 by 12 inch and main steel bar is 4 by 9 bar is I already discussed. FC dash is equal to 3.5 KSI and Fy is 50 KSI. And D is equal to 20 minus 2.5. This is total 20 and 2.5. So D will be equal to 20 minus 2.5 equal to 17.5. And D dash here, this is D dash equal to 2.5 inch. Now the question is to determine first PB, MB, and EB. PB is the balance load capacity, balance moment capacity, and balance eccentricity. Second is point P and MN for the a representative point in the tension failure region. Now, the case could be pure compression, pure tension, and a balance. So the first one is for balance. The second case is for the tension case. So for the tension case, we will provide C greater than CB. When the C value, C is the neutral. So the second case is about tension, and the third case is P and Mn and a representative point in compression failure region. And the fourth point is the axial load per zero eccentricity. So we should do all the four cases for balance eccentricity, for tension case, for compression case, and for the zero eccentricity. Zero eccentricity again mean in the load applied exactly at its center. Now, for the first case, PB, MB, and EB mean balance failure condition. So for balance failure condition, we have equation PB is equal to 0.85 C dash into BA plus AS dash FS dash minus AS into FS. This is a general equation. So for a balance failure, we have this equation. This means that we have compression at its center, steel come under tension, and the right side steel come under compression. So the equation will be like this. This is equation for the load. This is equation for the moment. We already discussed this equation. And for CB, C balance point, we will be using this equation, epsilon U divided by epsilon U plus epsilon Y into D. Put V 0.003 plus we have got 50 steel. So 50 by 29,000 multiplied by D is 17.5. So it will be equal to 11.11 inch. So balance neutral axis depth is equal to 11.11. And AB will be equal to beta 1 into CB. So beta 1 is 0.85 into 11.11. That will be equal to 9.44 inch. Now check whether compression steel yielding or not yielding. So we have this equation for stress in compression steel. We already discussed this equation, just put value. It will give us a value of 67.4 KSI and we have steel here 50 KSI. So this is greater than this, mean steel is yielding. And we will take Fs dash, this Fs dash equal to Fy equal to 50 KSI. So in case of